starting my lecture. Okay, now let's assume that we have a memory of, no, I'm not going to solve it. We have a memory of 64 MB, which is byte addressable. And then we have at least, let's assume at 8-way uh, cache of 5112 KB with 128 byte per cache line. How many blocks are there in, how many lines are there in cache, and what is the format of memory? We already covered some of the problem in our last lecture, but what I want to do, so I want to give you a more detailed explanation of this topic. So please, I want your attention, and most of the question that I will ask in my midterm will be similar to the question that I will solve now. Okay, so please, and then we'll have a lot of questions, question 1, question 2, and please, if this session is more and more interactive, I will ask easy question. So please, I want the session to be more interactive. Please help me. If you will help me, I will help you. Okay, now we are going to solve this question. Okay, now we are having a memory of, now I'm using a memory, now I'm going to this memory size is equal to 2 for a cross d. Am I right or not? Help me. Yes. What is my memory size here? Can you see here? What is my memory size?
64 megabyte.
Okay, 64 megabyte. And then we can say which is actually a 2 for a cross d, and d is 8 now. So now this 64 is actually, now if you do it, so now I'm going to different colors. So this 64 is actually what? 2 for 6. Okay, I'm trying my best. I'm trying my best so that you understand everything. 2 for 20, and byte is actually, can you see here, multiply by byte is actually 2 for 3. This is actually what? So now I'm now looking at the right side. This is actually 2 for a cross 8. Okay, so now what you do, this 8 and this 2 power 3 will cancel out, and now what is a here? Now a will be 26. Any question? Clear or not clear? So now the number of address lines, so the number of address lines, so what will the number of address lines, if I say okay, what will be the number of address lines? So the number of address lines is now a. So now we can partition this a into 3 field. Clear? So now we will have this 3 field, which is actually the offset field, the index field, and the tag field. Okay, so this a is now what? Help me. This is clear or not clear?
Yes, clear.
Yes.
Okay, now can anyone, that's very, thank you very much, thank you very much, thank you very much. I believe me, if you will answer me very quickly, I will be very happy, and if I'm very happy, your exam will be easy. Okay, now how many bits will be required for the offset? Can you tell me? So let's assume this is my offset b bits. So b, how can we compute b? Yes, b is what? Help me. Log 2 of what?
128.
Yes, it is actually log 2 is the byte size, the block size. And now what is the block size? It is actually log 2 of the block size, which is actually 128. Please remember, I'm now using a thing. So now can you see here, it is actually log 2 of 2 for 7, and b is now 7. So now b is now equal to 7. Any question? This is clear or not clear? Please don't write a message, please.
Yeah, it's clear.
That's very good. Thank you very much. Okay, now, so now the another question is this. So basically, okay, now we want to find another thing which is actually n. Okay, now what I'm going to do, so now we can see here, control C and control V. So now we can see the number of, so now the question is how many blocks are there in the memory? So the number of blocks, I call this as an n, is equal to the number of blocks, which is actually n, is equal to the memory size divided by the block size. What is the memory size? So the memory size is in the, now I'm now using some colors. So the memory size is 64 MB. So this is the memory size. I'm using a red color, 64 MB divided by the block size, Now I'm using what I'm going to do. So I'm now going to use green color, not green color. Green color is much better. In 128 per byte line. So this is 128 byte. So can we solve it? So this is actually 64 multiplied by 2 to the power 20 multiplied by b is equal to 2 to the power 7, which is 128 multiplied by b will cancel out. This is equal to 2 to the power 6 multiplied by 2 to the power 20 divided by 2 to the power 7. And then can we see here? So this is 2 to the power 26 divided by 2 to the power 7. This is equal to 2 to the power 19. And if we go for this 2 to the power 19, it is actually 2 to the power 9 multiplied by 2 to the power 10. So this is actually 5, 1, 12, and 2 to the power 10. Please remember this 2 to the power 10 is 2 to the power 10 K box. Any question? Got it or not got it? Okay. Now, another question. So now can you see here, now we have this main memory. So now what I'm going to do, so now please remember, what is now the address lines here? How many address lines are there for the memory? 26. Please, A is now 26. Please remember now what I'm going to do, and because you know this is a big problem, I could have solved very easily it on a board, but now because I need to use that. So now A is 26. We already computed A. So A is 26. So A is 26. So now this is my memory map. So it's A is 26. So how can we partition this into the address? So this address can be partitioned is like 4, 4, 4, 4, 4, 1, 2, 3, 4, 5, and 2. What is the maximum of 4? F, 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 F. And what is the maximum of 2? This is 1, 1. This is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So if we convert this, so how many bits are there? 4, 4. Okay, we also need another 4. 1, 2, 3, 4, 5, 6, 1, 1, 1, 1, and then we need an F. Am I right or not? Clear? So what's the minimum address? So the minimum address is actually 0, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is the minimum address. What will be the next address? So this is what? Byte what? Byte 0. What will be the address of byte 1? The address of the byte 1 will be 0x00000001 and so forth, so on. And what is the address of byte 2? This will be 0034562 and blah blah blah. What will be the address of the last byte? Can you even tell me? The address of the last byte will be actually 3123456. The last byte. And what is that last byte? Can you see here? So basic A is now 26. So if A is equal to 26, so how many bytes will be there in main memory? Can you tell me how many bytes will be there in memory? So there will be 2 to the power 26 bytes in main memory. And the last byte will be actually byte number what? 2 to the power 26 minus 1. And this byte will be what? Byte number what? 2 to the power 26 minus 2. And what will be the address of byte 2? The address of byte second last byte will be 3FFFFE. So if I ask this question in the exam, so okay, please remember, if I ask this question, so this may be the question in the exam. So the question 1 in exam may be, I will give you an address line and you can say, okay, what is the address of second last byte of this memory? Yes. What is the answer? 0x3FFFFE. Clear or not clear? Question number 2. This may also be the question.
It's not the
yes.
cache, right? This is the memory.
This is the memory. Yeah, this is not the cache. I'm not talking about cache. This is memory now.
Yes.
Yes. Though. Okay. Now. This is now my this memory. Did I write any cache here? Did I write cache?
No.
No. Okay. Now question number 2. This may be the question. This may be the question, and because I will give you this question, and and I will also tell you, I will give you half points for the correct answer and half point for the explanation. Question number 2. Question number 2. What is the address of the fifth last element? 1, 2, 3, 4, and 5. What will be the address of the fifth last element of the array? Can you tell me? E, this will be D, this will be what? C, this will be B. So what is answer? Help me.
3 FFB.
B. Got it? So these are the, whatever the question that I'm solving it here, I'm not only covering now the memory design problem, but I'm also covering the cache problem. Clear, Kenan? And now I will do all of these things. I'm going to have a practice session for all the questions once at a time. Any question? Any question? And if you want, I can have another practice session on Friday, but that will be optional. That will be optional. I will not allow you to, like, you know, but if you want to delay the exam until Saturday, this all depends on the students. Okay, now another question. So now the other questions. So we have now the same questions. How many lines will be there in the cache? Can you tell me? How many lines are there in the cache?
It's 512 kilobytes divided by 128.
So how many number of lines? So the number of cache lines will be equal to the cache size, which is in the red color, divided by the block size. And the cache size is actually, and I call this number of cache line, I can give any name to it. I can call it L, I can call it M, whatever you like, it's up to you. But what I do call it, I call it as L. So what is L? It is the cache size. It is actually 512 kilobyte divided by the block size, which is actually 128 kilobyte. Okay, so this is actually 2 to the power 9k divided by 2 to the power 7. No, the block size is byte. Kilobyte divided by 2 to the power 7 b will cancel out. So this is actually 2 to the power 9. It is 2 to the power 10 divided by 2 to the power 7. This is actually 2 to the power 19 divided by 2 to the power 7. This is actually 2 to the power 12. And if it convert this, it is actually 4096 lines in the cache. Please remember, this is now total lines in the cache. Any question? We solved the question before, but these are 4096 lines in the cache. I'm also recording this lecture, so please go through all of these things. So now these are the total number of lines, but this does not imply. So please now remember. So now we have, remember, if you remember in the last thing is, we can say, so we had the number of, so we have in sets. Remember, in the sets we have some sets. We have set 0, we have set 1, we have set 2, and blah 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 until we have set s minus 1. Remember, how many sets are there? So total sets are, total number of sets are what? S. And how many lines are there in the cache? So there are A lines. So there are A ways. We can call it A's, ways, or lines. So there are A or ways or lines in a set. So each set consists of lines A0, A1, sorry, control C. So sometimes this, clear or not clear?
Clear, Professor.
I'm sorry, something happened with me rapidly. I think something strange happened and everything. I lost everything. Sorry. Okay, how many lines were there? Total number of lines were there. How many lines were there?
2 raised to 12. 2 raised to 12.
The total number of lines that we calculated it. So this will be 2 to the power 12 lines in the cache. And if you look at the cache, so cache consists of set 0, set 1, and blah 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 until set s minus 1, and each set has way 0, then way 1, and how many lines are there? Way a minus 1. So how many lines are there in the set? Help me. A lines. Okay, so how can we calculate s? What is s now? Can you even tell me? How can we compute s?
We divide total number of lines by the mapping, which is 8.
Yeah, so if we say that there are total lines, which is actually L is actually 4096 now. So how can we calculate S? L is equal to the total number of lines is equal to S multiplied by A. Got it or not got it? So the total number of sets, each set has A lines, so the total number of lines is L is equal to S multiplied by A. And how can we calculate S? L divided by A. What is L here? 4096. What is A here?
8.
What is A here now? Please help me.
8.
So A is 8. Associative is 8. Can you see here? We are 8-way associative. So it means that A is 8. So then it will be 2048, 1024, and 512. So what is S here? S is 512. Now we want to find the index bit. What is K? The index bit. The K is actually log 2 of S, which is actually the log 2 of 5112, which is actually the log 2 of 2 to the power 9, which is actually 9. So how many bits will be required for index? How many bits? Help me.
9.
9. So now please remember we go for this. So now this is the whole thingy. So now I'm copying it from here. So now we already calculate the B here. So please remember, now in the previous thing we calculated B. How did we calculate B? Remember, B was actually the log 2 of the log 2 of the block size. And now we need to calculate K. I'm now using the thing. So this is actually K, and K is now the log 2 of the number of set, which is actually S. And now here, what is S here? So S we already calculated is 512. So we need 9 bits for it. So K is now 9. Any question? How many bits will be now required for the tag? Yes. Let's assume this is T, which is red color. Yes. Anyone may answer. Please help me. What is T? T is equally A minus K minus B. K is now 26. K is now 9. And B is now 7. So T is now 10. So now this is now. Any question? Is it clear or not clear? So this may be the question in exam. So actually, I may give you the problem. So this may be the question in exam. So the question in exam is, this is the question in exam. So this may be the question in exam. I give you the problem. Find the format of the main memory block address. So this is now the question, and now this is the answer to this question. Any question? Is it clear or not clear?
Clear.
Clear. Okay. Now, how many main memory blocks are there in the main memory? How many number of blocks are there in memory? Please remember, 512K blocks. 512K blocks. So now I'm going from the block thingy. So now if you go from here, so now memory, we can have main memory block 0, in main memory block 1, and blah 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 blah, and maybe main memory block 15, and blah blah blah, and until main memory block 511, and main memory block 5112, and blah blah blah, and main memory block 600, and blah blah blah. So now this is just like the main memory blocks. How many total main memory blocks are here? Please, we already calculated it. How many number of memory blocks are here? We already calculated it. Help me. So the number of memory blocks are 2512K. So these are 512K. So the last block will be main memory block 512K minus 1. 512K, it's actually 512K multiplied by, so this is actually the last block will be main memory block 5112 multiplied by K is 1024 minus 1. So if you convert this into binary, you will get the answer. Okay, now in this example, how many sets do we have here? How many sets do we have? What is S now? 5112. So it starts from which set? Can you tell me? It starts from set 0, then we have set 1, then blah 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 until what? Set 511. So can you see here now we have the mapping of this here. We have set 0, then we have set 1, then we have set 2, and blah blah blah. Then we have set 15 and blah blah blah. Then we have set number 511, and then we have set number 51. No, we don't have any sets. These are all the sets here. So okay. So now what I'm going to do, so now I'm going to do insert this. Clear or not clear? Any question?
Clear.
Okay, now which block will be mapped to set number 0? Can anyone tell me which block will be mapped to set number 0? Help me. So this
Block
may be the
0?
question in exam. Yes. So basically, which block will be mapped to set number 0? Now this may be, now what I'm going to do, I'm going to give you all the question in exam. So the block that will be mapped to set number 0 is MB0. Which block will be mapped to set number 1? MB1. Which block will be mapped to set number 2? MB2. Which block will be mapped to set number 15? Help me.
15.
MB15. And blah blah blah. Which block will be mapped to set number 511?
511.
Clear? Okay. Again. So this may be the question in exam. So please, I'm saying it's okay. So okay. Okay. What about this block? Where this block will go? Yes.
What number is it?
MB 600. Okay. Now this is the, so this may be the question in exam. Where MB 600 will be mapped. This is the question now. This may be the question in exam. So I will give you this question. I will give you the same question. All the question you need to identify the number of sets. You need to identify the number of main memory blocks, and then you can tell, oh, where MB 600 will be mapped. So this may be the question in exam. Okay. Now again, now I'm going to do. I'll explain it. I'll explain it now. No problem. I'll explain it. So I need your attention. Which block will be mapped here? MB what? Help me.
512.
512. Which block will be mapped here? MB 513, MB 514, and blah blah blah. Which block will be mapped here? Okay, now please look at here. So this block, the block that will be mapped to here, it's 0, 5, 1, 12, and then MB what? Help me. The next block. So we are adding plus 5, 1, 12 here, and then we are adding plus 5, 1, 12 here. So if you are adding plus 1, the next block that will be mapped here 1, 1, 0, and then we add another 5, 1. It will be what? MB what? Help me. So 1024 plus 5, 112, 1536, and blah blah blah. Any question?
No.
Now, okay, which block will be mapped here? The next block that will be mapped to set number 15, the second block.
512 plus 15.
Very good, very good. That's the reason. That's the reason. It means that you're getting. So now if we add 512 with 15, so 512 is 7, 2. So the next block that will be sent at MB 527. And the next block that will be mapped to MB 15. Can you tell me?
527 plus 512.
So 527 will 55 and 12. So the next block 729, 3 and 1039. Got it or not got it? Any question? And which another block will be mapped to the last block, the next block? MB what? Help me.
1023.
Yes, because it is 1023 and here it is 1024. So it will be 1023. Got it or not got it? This is clear or not clear?
Clear.
Okay. What will be the another block that will be mapped to the last block, the next block?
1535.
15 what? 15. Very good, Yasir. Thank you. Okay. Now the question is this. Okay. Now if now this is another question. So this is another question. Okay. Okay, what will be the now this will be another question in exam. Question number 1. Question. What will be the tag of what will be the tag? And please remember, for every question I will also have 2 questions: the correct answer and the logical explanation. So half points will be for the correct answer and half points will be for the correct explanation. What will be the tag of MB 1039? Can anyone answer me? Answer. Looking at the figure. How many bits are required for the tag? Please look at here. How many bits will be required for the tag?
10.
10 bits. So what will be the tag? So the tag for so the tag for MP15 will be actually its tag will be. So can you see here? So now what I'm going to do? So now please look at here. Now I'm going to do it in another thingy. And I'm going to explain it here. This is very important. Okay, all of these blocks are mapped to which? All of these blocks are mapped to set number 15. So what will be the tag for MB15? The tag for MB15 will be 0, 0, 3, 4, 5, 6, 7, 8, 9, 10. 10 bits. This tag is 0. What will be the tag for MB512? Can you tell me? Help me.
1.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The tag will be 1. And what will be the tag for this? Anyone help me? 1, 2, 3, 4, 5, 6, 7, 8, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Please remember, all of these tags are in binary. What will be this tag? Clear or not clear?
Clear.
Okay. Now, again, another question. This is a $1 million question. So what I'm going to do? Let's assume we have another set. Let's assume we have another set. Let's assume that set is set number 30. Which block will be mapped here? Can you tell me?
MB30.
MB what? Tell me. MB30. Then
MB542.
Yes, MB542. So 542, and if we add 512 here, so this will be 4, 5 plus 4, 5, 1054, and MB 1054. And if we add 512 here, it will be 6, 6, 5, 1. So MB 1566. What will be the tag of this thing? Can you tell me?
All zeros, then 1, 1. So 3.
3. Very good. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 1. So this tag will be equal to 3. Any question? This is in binary and this one is in decimal. Any question? Clear or not clear? So this is actually 0 of 10, this is actually 1 of 10, this is actually 2 of 10, and this will be any question. Got it or not got it? Okay. Can anyone tell me what about MB? No one answered me this question. Where 5 MB 600 will be mapped?
So it will be in the second iteration or the first tag.
I know that,
Somewhere
but
there.
is there any formula for that?
There is, I think, but I forgot.
Yeah, but that's the question that I'm asking. So now what I'm going to do, this is a tricky question. So basically, why I'm going to do that, because once I will have a lot of students will send this the question for me to some experts, and they will answer the question. But there will a lot of question that I will ask. Only the students who attend all my lecture will be able to answer this question. Okay, now the thing is, so now what is my next question? So my next question was, do we have some? Okay, no. So now I'm going to make a logical argument now. Okay, now basically, so now this is main memory block 0, then we have main memory block 1, and blah blah blah, and main memory block 15, and then we say main memory block 600, and then we have main memory block 1024, and blah blah blah. There are a lot of blocks from main memory, so I'm not going to know. Okay, now we having the same argument. Which block are mapped to set number 15? Can you tell me? Anyone? Yes. 15. This one 527. The other one was 1039. And blah blah blah. So there will be some index set number I, and we don't know, and I want to show that which block will be mapped here. So the block that will be mapped here, it will be set number I. Am I right or not? What will be the other block that will be mapped to set number I? Can you tell me? Which block will be mapped here?
Plus
It will
512.
be MBI, and MB what? Help me. I plus what? Help me.
512.
Plus 512. Got it or not got it? Okay. So now how can we compute this set number, set ID? So can you see what will be the set ID? And please remember, I told you the formula in the last example. What will be the set ID? So the set ID is actually, there are two methods to it. It is actually the main memory block number mod, remember, the number of sets, mod S. Got it or not got it? So okay, now please remember now. Okay, now if you say, okay, now let's assume we want to have the set ID for MB15. So now let's assume I want to say, okay, where MB15 will be mapped? Where MB15 will be mapped? I want to find the set ID. The set ID will be, the set ID I will be, can you see? The set ID will be actually 15 mod, and how many sets are there in this example?
512.
512. If you take the ampersand operator, so it will be 15. Okay, now I'm solving for MB527. How can I find I? I is actually 527 ampersand 512, which is actually the number of sets. Okay, S in this example is 512. Got it or not got it? Okay, now if we divide this 527 with 512, 512 multiplied by 512 is 512, and then if we remainder, this is 15. So this is actually mapped to set number 15. Any question? Okay, so what about MB600? Can you answer me now? Anyone?
88.
88. Very good, very good. That's the thing. So now where, so now okay, the question is where MB600 will be mapped. So 600 will be mapped. So now we want to find the index I, which is actually 600 in percent S, and S is now in this example is 5112, and it is actually 88. Why 88? This is 600, and now we have 5112, 1 divided by 5112, and the remainder is 88. So it will be mapped to, so MB 600 will be mapped to set number 88. Got it or not got it? Okay, this may be another question in exam. So I'm telling you a lot of question in exam. So these are the question in exam. So another question. I'm again saving it because I don't want to lose all of the work that I did. Okay, another question. Okay, which main memory block will be mapped to set number, which main memory block will be mapped to set number 88? So now this we have set number 88. Which block will be mapped here? Help me. MB88. What about MB what? Help me.
512 plus 88.
This is 600. We calculated it. Okay, and then we say 600 plus 512 and 2, 1 and 6, 1. So it is actually MB 1112 and blah blah blah. Got it or not got it? Okay, now in this example, okay, now what is now the tag of MB60? Can you tell me what is this tag? What will its tag? Can you tell me? So this tag, its tag will be 1, and what will be its tag? Its tag will be 2. But how can we find this tag? How can we find this tag from the main memory block number? Can you tell me how can we find this tag? Yes. Can you tell me? This is very important. So how can we find this tag? So the tag can be found is equal to, this is important. So the tag can be found by using the main memory block number divided by, okay, divided by the number of sets. Okay, now, okay, we want to find the tag for, now we want to find the tag for using a formula. We want to find the tag. We want to find the tag of 600. Okay, so what is the main memory block number? So it is actually 600 divided by 5112. So now we divide this 600 with 5112. Now we have 5112 multiplied by 1 is 512, and it's the remainder. So the remainder will now tell me, can you tell me? This remainder will tell me what? The set ID, and the quotient will tell me. Can you tell me what will the quotient tell me? Help me.
The tag.
The tag. Got it? And now I'm going for 1112. So 1112, and I want to divide it with 5112, which is actually the total number of sets. So it is actually 251. It is 1024, and it is 8, and then this is 8. So the quotient here, the remainder here will give me what? Help me.
Set ID.
Set ID. And this thingy will give me what? Help me.
Tag.
Tag. Okay. Now there is another. This is one thing. This is how do we compute the tag, and now I'm giving you $1 million question. $1 million. Anyone who will answer this question in 10 seconds will get 1 bonus mark. And I will answer this question. Please remember, I will answer this question in 3 seconds. Got it or not got it? I can answer this question in 3 seconds. So I am giving you 10 seconds. Anyone who will answer this, and please, this is 1% of your evaluation. Okay. Assume. Now we have an address. So what I'm going to do now, I'm going to save it because I don't want to lose the work. Assume that we have an address. How can we partition the address? How many fields do we need to partition this address? Please, I want this session to be more and more interactive. Yes. Yes. How can we partition this main memory address? Can you tell me? How many fields? The T field. Got it? The index field and the offset field. Got it or not got it? Okay, let's assume. So there will be 2 questions. Anyone will answer this question in 10 seconds will get 1 bonus mark. So let's assume if you have this number, and all these numbers are in binary. Question number 1. What is the main memory block number? Now your time starts from now. Yes. This may be the question in exam. Okay, question number 2. What is the set ID? Question number 3. What is the byte number? Question number 4. How many sets are there? So these are all the questions of exam. Can you answer me any of the question? Yes.
Is it 11 times 10
Which one?
for the first one?
11 times what?
10?
No.
The
Okay,
memory.
now I'm going to answer now question. Okay.
Professor,
What
I
is
know.
the set ID?
Professor, I know.
Yes, what's the answer?
The block number is, which is TK. I think, I don't know if I made computational mistakes, but I think it's block 186.
Okay, I will answer it. Okay, can you tell me what will be the set ID? What will be the set ID? This is very
10.
10. The set ID. So now it's the green color. So it's a green color. So what I'm going to do, so in the green color, so this is actually 1010, and if you convert this into binary, this is actually 10. So the set ID is set number 10. Because this is, got it or not got it? What is the byte number within the block? Okay. Okay, this is also 10, but okay.
The offset.
Now this is the offset. So the byte number within thing. So maybe I will make it like this. So maybe I'll make it like more thingy. So I'll make it like I put a 1 here. So the block number, so 1 2 3 4 5 6 7. So what is the byte number? So the byte number is actually 1 0 0 1 0 1 0 1 2 4 8 16 32 and 64. So this is actually 64 plus 8 plus 2 72 74. So the byte number is byte number 64 within the block. Got it or not got it? So can we convert this into binary? So this is the byte number. Any question? How many sets are there in cache? So how many sets are there? So the total number of sets will be, can you answer
74
me?
now, Professor. 74,
Huh?
not 64.
70. Yeah, 74, yes. How many sets will be there in the cache?
16.
Yes, it is actually 2 for k. K is 2 for 4, it will be 16 sets. And what is now the main memory block number? So the main memory block number, so now I'm going to answer this question. So the main memory block number, so I already did it in the last thing. So what I'm going to do, so I'm going to copy this and I'm going to paste this. Okay, so the main memory block number is found by concatenation of T and K, and notice T is 0 1 0 1 1, and then T and K, which is actually 1 0 1 0. So this is actually 1 2 4
Professor
8
186.
16 32 64 128 and 256. So this is actually, can you see here, it is 64 plus 32 plus 16 plus 8 plus 2, so 96. What is the number? 101011. So 10, so 1 2 4 8 16 32 64 128. Oh no,
Yeah, so it's
1
186.
4 8 16 32 64 128 and 256. So this is actually 128. Got it? So 128 plus 32. What's 128 plus 32? Can you tell me? 30, 60,
160.
160, 176, 170. Yes. No, this is actually 160, 176, and what? 186. Yeah, am I right?
Yes, Professor.
Yes. So this is actually the main memory block number. So this is actually main memory block number 186. So these are all the questions that I can give you in the exam. Okay, another question. Another question. So now this is another question. How many blocks can be mapped to a particular cassette for this main memory block address? This may be the question in exam. Anyone? Yes. I'm expecting an answer from you.
You mean like in one set? How many blocks?
Yes. And how many blocks can be mapped to a particular set, any set? So it will be actually, the answer is choose for T. And what is T here? So 32 for this example, 32 main memory blocks can be mapped to a particular cassette. Question number 2. Okay, now this is question number 1. How many blocks can be mapped to a particular cassette? So it means, and I already explained this in my last lecture. So that's the reason, you need to keep track of all the lecture. And every example is this. For this example, question number 2. Question number 2. How many blocks can reside in a cache set at a time? What is the answer? Okay, there are 32 memory blocks that can be mapped to a particular cache set, but how many of them can reside in the cache set at a time? Anyone may answer.
Is it the number of ways or lines?
Very good, Yasir. That's the reason that now you're paying attention, and I'm very happy for this. It means that A ways, because enough information is not given, so it means that A lines can reside in a set at a time. A's line can be, okay. How many blocks can be mapped to a set? Can be mapped to a particular set? It is actually 32. Okay. Now, what should be the relationship between A and 2T? Can you tell me? Should A should be greater than 2T, or A should be smaller than 2T, or A should be equal to 2T?
Less
Yes.
than or equal?
No. A should be very much equal to 2T. Why? Because if A is equal to 2T, it means that now the memory size and the cache size is equal. So A has to be very less than. You got it or not got it? So now can you see here? Now I've explained this one in an example. Why I'm doing? So basically, can you see here now in this example? We have many blocks can be mapped to a particular set. So in this example, what was T? What was T here? It means that what was T here? T was 10. Since T was 10 here, so this implies that how many blocks can be mapped to a particular set? So the question is this: how many blocks can be mapped to a particular set? Here it is 2 is for T, and 2T was here 2 is for 10. So 1024 blocks can reside in this cache set, can be mapped to a particular cache set. But how many of them can reside in a set at a time? How many in this example? Because in this case, what was A here? A was 8. So only 8 can reside in a set at a time. And this A has to be very less than 2 to the power T. You got it or not got it?
Yes, clear.
Any question? And please remember, this whatever the question I'm asking is, they are very important for your midterm ahead. And please remember, I will not allow backtracking. You know the reason I will not allow backtracking, whatever the reason is, but I will not allow backtracking. So backtracking is not allowed. And this will be very tricky and very logical question, and this question will be only for the students who attended all my lectures. Okay, now another question. Please remember the question that I'm going, the question that I'm going it is all, the question that I'm now answering it is all relevant to your midterm. Let's assume we have a cache here. And this is actually set number I. And this set number I contains of 2 ways, which is way 0. This is valid bit is 1. The tag bit is 101. Okay. And this is the data bits. So B0 until B31. And then we have, this is way 0. Then we have another way 1. And the valid bit is 1. The tag is 010, and it is actually B0 until B31. Got it or not got it? Any question? So now the question is, now this is the, and this may be the question in exam. So please, I want your attention. I want your attention. If this is the main memory block address, which is divided into 3 fields, namely the key field and the index field, in the block offset field. Okay, and this value is 010, and this one is 11010, and the block offset field is 0. And now if the byte offset is 10101. Okay, question number 1. What is, let's assume this address is mapped to set I. What is the value of I? Can you answer me this question?
52.
Very good, Yasir. I think you took digital system with me now. That's the reason that you are answering my question. Yes.
No, Professor, calculator.
Calculate. Okay, but still it's good. Okay, so what is the value of I? So the value of I is actually, you need to look at the index field. So the index field, so now I'm going to the value of I. So this is actually 1 1 0 1 0 0. This is actually 1 2 4 8 16 and 32. So actually like 32 plus 16 plus 4, it is actually 52. So what is I? So if it is mapped to it is actually now set number 52. Any question? Question number 2. Is there a hit or a miss? Yes. Anyone may answer. Is there a hit or a miss? I'm not getting any answer from anyone.
Hit.
Why?
Because there is the tag 010.
Yeah. So basically we compare this tag. So we compare this 010 with two tags. 101, which is this one, and the green one. Zero 10, which matches. So now these two matches. So it means this matches. It means that this block is now residing in this thing. Got it or not got it? So it's a hit. Yes, it's a hit. It's a hit in way 0 or way 1?
Way 1.
In way 1. Question number 3. What is the byte ID? Byte ID 10101. So it is actually 1 2 4 8 16. So the byte ID is 16 plus 4 plus 1. The byte ID is actually byte number 21. Got it or not got it? Okay. Question number 4. What is the main memory block number? Anyone may answer. What is the main memory block number?
You
Can
put
you
T
tell
and
me?
K together and calculate the
Yes,
number.
T and K together. Very good. Yasir, very good. Thank you. Thank you. So basically we put T and K together. So it will be actually 0 1 0 1 1 0 1 00. So 1 2 4 8 16 32 64 128. So 128 plus 32. What is 122? 8 plus 32. 160. 160 plus 16. 176 plus 1, it is block number 180. Any question? Any question? So please remember, today's lecture is included. Today's lecture is included in the exam. I'll save the working and then I will post all the working on iLearn. Okay, so if and then I will answer many of your questions. Okay, please remember, I already posted some most cache practice problem on iLearn. Please also go through all these questions on iLearn. After the lecture, I will tell you how to prepare for the exam. Okay, so now if you look at here, now we have a level of hierarchy. So register are the faster or smaller, cache is the faster memory, which is used in between the processor and main memory. Got it or not got it? So now what I'm going to do, so I'm going to put this not writing anything now, so I'm removing this thing. Is the screen visible to you now? Anyone? The screen visible to you or not?
No, not yet.
Okay, so now I'm going to share my screen. Now is the screen visible to you now? So here is the hierarchical memory organization with processor. Processor is we have register, which is the register are very smaller, and then register the fastest. Cache is the faster memory, which calls the SRAM, and DRAM make good memory because it's bigger. Okay, so now what we are going to do, so this is better for majority. So now we can see, so now we have different levels of cache, level 1 cache, level 2 cache, and then we have main memory, and then we have the secondary memory. So assume that we have multiple level cache. So we have level 1 cache, level 2 cache, then we have the main memory, and then we have the secondary memory. Okay, now the question is that, I will explain this with an example. Let's assume Yasir wants a Coke, and you want to drink a Coke. Okay, so first Yasir will go into his fridge and see in the fridge, oh, whether Coke is available or not. If it's not in the fridge, this is level 1 cache. If it's not in the fridge, then he will go to Sharjah Coop at AUS, which is smaller. If the Coke is not there, okay, then he will go to the main memory, which is actually the Sharjah Coop outside, which is bigger, and the secondary memory is much bigger. Can you see? If we go from the top to bottom, so which one is faster? Processor is faster, or L1 is faster, or L2 faster, or main memory is faster? Can you tell me? Which one is faster?
Processor.
Help me. The processor is faster. Okay, let's assume. Okay, now I will give you another example. Let's assume Yasir wants to read a book. So we'll go to his table. If the book is on the table, okay, he will read it. It will access it from L1. But if it's not on the table, he will go to his rack, which is L2. He will go to the rack and find the book there. But if the book is not there, he will go to the library. Okay. And if it's not in the library, he will go to the Amazon and order it. So these are 4 levels of hierarchies. Got it or not got it? So the level which is closer to Yasir, which is actually the rack, which is smaller but faster. No, not the table, sorry, the table. L1 is like the table. Then if it's not there, he need to go to the rack, because going from the table to the rack, it takes some time. So L2 is like more latency, but bigger. If you go to the main memory, like your library, finding a book in library will take more time, but it's bigger. It can accommodate a lot of books. And the secondary memory, which is actually the Amazon or thing like that, so it's much bigger. But the thing is, you need to find it more. You got it or not got it? So the number of bursts data transferred from the process from the L1 to the processor is bytes, and then we need to bring the data from the L2 to L1, which is in the block. And if you want to transfer from the main memory to L2, so we transfer it in the presence of like more blocks. We call this as pages. And now from the secondary memory to the main memory, we transfer it in the level of page. Any question? Got it or not got it? So now if we increase the distance from the processor, it increases the access time. Okay, so cache, can you see here, register are much faster. And how much latency the register take? It takes 1 to 2 clock cycles. What's the cache? The cache range is typically from 64 kilobyte to 1 megabyte. It is 4 to 10 clock cycle. And the memory, which is much bigger, it is in gigabytes, in 150 to 500 clock cycle. And then we have the hard disk, which has the terabyte. It takes more clock cycles. Any question? Should we proceed? Got it or not got it? So now this is a computer system. So it consists of some input devices like keyboard, output devices like monitor. We have some central processing unit, that the processor, and memory. Memory stores instruction and data. And now we have an address bus. Then we have the data bus. Address bus is your the address lines. The data bus is your data lines, and the control bus. These are different type of control signals like read write bar, address strobe, output enable, and write enable. And we cover all of these in more and more details. So this is the computer system model. So now these all the thing. And there are different type of memory. So this is the primary memory, which is the RAM, static RAM, the dynamic RAM. These are different type of memories. And now we have the cache here. Got it or not got it? Okay, now the cache is like this. So let's assume we have now the cache, and now this is single level cache. Let's assume if processor wants to process some data from the cache, it will look into the cache. If it's there, it's faster. If it's not there, it will go to the main memory. But now if we have a CPU and we have different levels of cache. So first we will look into the level 1. If it's in level 1 cache, it is accessed much faster. But if it's not there, it will go to the level 2. And this is relatively fast, but not the fastest. The fastest is level 1. But if you look at here, level 2 is fast. But if you compare it with level 3, so level 3 is less fast. And the main memory is much slower. So when you go up to the hierarchy, the size becomes bigger and bigger. Since the size has become bigger and bigger, so the latency will be more. Why the latency will be more? Because finding an element in a bigger space will take more time. Got it or not got it? Anyone who will answer me this question will get 1 bonus mark. Why? Because I already taught you this topic. This may also be the question in exam. Why bigger memory has more latency compared to smaller memory? Can you answer me?
Because it has more cycles?
No. Why? Anyone who will answer this, because I cover this problem in the memory system design. Yes. Anyone may answer. I will give you 10 seconds. Anyone who will answer this question will get 1 bonus mark. This may also be the question in exam. Why bigger memory has more latency compared to smaller memory? Yes, Tira. Yes, Insia. Yes, Hamdan.
Sorry, Professor, I didn't hear your question.
Why bigger memory is slower compared to smaller memory? Let's assume we have bigger memory.
The latency is higher, so there's more
64
cycles.
MB. Why?
Because the latency is higher, so there's more cycles.
Why? That's the question. Why it's higher? Why?
There is more decoder?
Yes, Yasir. Yes, safe. Very good. Yes, very good.
Has higher decoders?
Very good. Now that's the good answer. That's the answer. Because the thing is, so let's assume if we have bigger memory, we need bigger decoder. Remember, so let's assume if we have 8 rows, we need 3 to 8 decoder. If we have 16 rows, we need 4 to 16 decoder. If we have 5 rows, we need 5 to 22 decoder. So the greater the size of the decoder, the more be latency. If you look at your decoder, what is a decoder? It consists of different gates. Let's assume if you have 2 to 4 decoder, what will be A0? It is A0, A1 bar and A0 bar. If you have 3 to 8 decoder, what will be M0? M0 will be A2 bar, A1 bar, and A0 bar. So the size of the gate will become bigger. And these are the gates with more fan-in. When there are more gates with more fan-in, it will have more latency. I hope I answered your question. Got it or not got it? So bigger memory has bigger decoder. And bigger decoder will require more gates. When it requires more gates, it will have more latency. So this may also be the question. So there will be a lot of logical questions also. Which you cannot find on ChatGPT, which you cannot find on anything. And if you hear to all of my lecture slides, you will do good. Any question? Okay, now And then we already did it. So okay, this is the set index. Okay, now this is the direct map, and we already covered the direct map, the set index, and blah blah blah. We covered all these things. I'm not going to explain this thing. Okay, so the index field will be identified to use to set index to a particular set, and the tag bits will be okay. How many comparison will be there? Can you tell me how many comparison will be there in a particular cache set? Let's assume if we index to a particular
Number
cache
of
set. This
ways?
may also be a question. Yes, yes,
The number of lines or ways?
yes, the number of lines. So if there are a ways, so there will be a comparison. If the number of ways are a, there will be a comparison. So if we have a two-way associativity cache, there will be two comparison. If we have a four-way associativity, there will be four comparison. How many blocks can be mapped to a particular cache set? 2 is to the t main memory blocks can be mapped to a particular cache set, and only a of them can reside in the cache in that set at a time. And this a is very smaller than t. And for this reason, the cache is smaller than main memory. Any question? Got it or not got it? Okay. So if we have a direct map cache and a two-way associative cache, and both are of the same size, which one will have less latency? Anyone may answer. Anyone may answer. Can you? So if we have a direct map cache and a two-way associative cache, both are of the same size, which one will have more latency, the direct map cache or the two-way associative cache?
Direct, because it's only one way.
Because direct will have lower latency. Why? Because we need one comparator. But for two-way associative cache of the same size, we will need two comparators. Got it or not got it? So that's the thing. So the t bits will be the thing is. Got it or not got it? Any question? So these are all the problems. Please go through all these problems. These are the problem I already solved it. So please go for these problems. So this is a problem. Please solve this problem at home. I'm going to save this now. And then I'm now making this, I'm stop recording, and then I can